Hello, welcome to Monday. We're looking at Chapter 4, Lesson 3, Rate of Change and Slope. And we're going to see the difference between the way we use those two phrases. If you'll join me on page 244, we can see that the rate of change is very significant when we talk about slope, but we can also see that rates of change can differ and not be constant, as we defined them last week. Rate of change is described as the ratio that compares the amount of change in a dependent variable to the amount of change in an independent variable. And you can see this definition right here. And we know that to mean delta y over delta x. Let's take a look at the check it out problem below example 1. It says the table shows the balance of a bank account on different days of the month. Find the rate of change for each time interval. During which time interval did the balance decrease at the greatest rate? So we're going to take these in groups of 2 ordered pairs, and we're going to go from day to day. So from day 1 to day 6. If you think back to our definition of independent and dependent, we know that independent variables are always time, and we're dealing with time here. So we do know time to be independent. So that's going to be our x value. Our balance depends on the day. The balance in the account depends on which day we're at. So let's take that change in y, 550 down to 285. And we get a 265. A change in y, our dependent variable, over now. This is the tricky part. We subtracted this way. We need to subtract this way. We can see it is going down. So on the bottom, 1 minus 6 is a negative 5. And when we simplify that, we get negative $51 per day. Per 1 day. That's the rate of change between day 1 and day 6. And we would continue, as per the directions, we would continue to find the rate of change per each set. We would go from 6 to 16, 16 to 22, and 22 to 30, finding 1, 2, 3, 4 different rates of change. So please go ahead and finish check it out problem number 1 and come right back here and I'll show you the solutions. So we can take a look at all of these rates of change. The final question was, during which time interval did the balance decrease at the greatest rate? And we can see that day 1 to day 6 at negative $53 per day would be the greatest decrease. Let's go ahead and take a look at example 2, finding rates of change from a graph. This is going to be similar to what we just did. We just don't have our data in table form. So if you look at the graph carefully, we see something roughly like this. And when I say roughly, I mean roughly. We're going to look at this first segment. Let's get something that's a little easier to work with here. This first segment from here to here. And if you look closely in your book, you can see that the cost per year for those years, 1988 to about 1990, there was 0 cents change over the years. 0 over anything equals 0. Remember, it's just 0 in the denominator that causes us problems. So we're going to go ahead and look at each of those different rates of change on the graph. In this next section, from here to here, we could collect data points off of the graph. This one's not listed very clearly, but we could take these data points, write them out as ordered pairs, and do the exact same thing that we did in the table on example 1. So it wants you to, in check it out problem number 2, graph the data from check it out problem number 1 and show the rates of change. We're going to skip that. I'd like you to look at the middle of 245. The know-it notes are this. The slope of a line is indicated by the rise, the difference in the y values, We've been over this. We know the rise is the difference, delta y, over the run, delta x. The change in the y over the change in the x. And we define this to be the slope. When we talk about a constant rate of change, we know we have a linear function. In the graphs that we were just dealing with, we saw that we had different rates of change, so we don't speak of the slope of those particular graphs. When we have different rates of change, we don't talk about a single slope. The easy thing about looking at the graph to determine the slope is that we can actually just count. So if we look, we understand we need the change in the y values and we need the change in the x values. We can simply count from our point 1, 1, 1, 1 to our point 2, 4. So we're going to do something quick here before you pay too much attention to it. I made a huge mistake, so we're going back and fixing that. We can do this in two ways. We're counting our rise, and we know from 1 to 4, we went up a total of 3 units. And when we go over, that's our x value, our run value, we went from 1 to 2. So let's take a look at that. Rise 3, run 1. In the case where we get some more complicated values, we would like to remember this definition of slope, and that's the change in the y values, y2 minus y1 over x2 minus x1. And we can quickly and simply put these values in of these ordered pairs. I'm going to use the top ordered pair first, bigger numbers. We have the change in y, 4 for the top point, and a 1 for the bottom point. So I see that change to be 3. That's matching what we had before. And my change in the x values, 2 minus 1, giving us 1. Same slope, 3 over 1. I want you to keep in mind that if you use y2, x2, that same related ordered pair has to be first in the numerator and the denominator. Check it out. Problem number 3 says find the slope of the line that contains the point 0, -3, and 5, -5. We're going to use that formula again. Slope is equal to y2 minus y1 over x2 minus x1. Let's label those. This could be x1, therefore this is y1, x2, y2. That's what I was indicating when I said they needed to match. So let's just plug those values in. y2 on the top, -5 minus y1, keeping track of that negative sign. And for the bottom, x2, because y2 is first on the top, x2 has to be first on the bottom, minus 0. And simplifying, -5 plus 3 is -2, 5 minus 0, 5, and we get a negative slope of 2/5. It's important to remember two of our very special lines we have. Those are nice and straight. We have two special lines. We have a horizontal line. And if we think about the change in y over the change in x, we can see that y value is not changing. It's a 0 change. But if we think of a line running, a line runs forever. So we just want to take a segment of this line. Let's say that we ran 3 units. In any case, horizontal lines always have a slope of 0. 0 over anything simplifies to 0. In contrast, we have his cousin. Let's look at this line. His cousin, what should we call him? Vern. Vern, the vertical line. So here we go. Let's talk about the change in y now. The change in y, just like we talked about that horizontal line, it goes up and down forever. So let's indicate an amount of the line that we want to talk about. That change would be 3. But our change in x, we can see the x value does not change. It remains at 3. Everywhere we go, it's negative 1, 3, it's negative 2, 3, and we can see that denominator, that change in x, is 0. And we know from experience that when we divide by 0 on our calculator, we get an error. This indicates that this line has a slope which is undefined. We talk about a vertical slope as undefined and a horizontal slope as 0. 2 more quick ideas to consider when we're looking at the graph of a line and we see that the graph is rising from left to right. We know that this has positive slope and positive correlation from our scatter plots. The other one we need to consider, from left to right, if we are decreasing or going down, we know that to be a negative slope. Things to keep in mind. If we're looking at a slope, calculating its slope, and we get positive when it should be negative, or negative when it should be positive, then chances are we need to look back at our math and recalculate.